Hello students, let us study about electric susceptibility now. So it is represented by chi. So we know that V0 is equal to V plus V dash that I have described in the last class. So where E is equal to V by D, so we can write V0 is equal to V plus V dash in terms of E also. So that is, this E is intensity of electric field, or we can tell only electric field. E0 is equal to E plus E dash. Multiplying throughout by epsilon naught here, we get epsilon naught E0 is equal to epsilon naught E plus epsilon naught E dash. Now this epsilon naught E0 can be written as epsilon naught E0 is V0 by D. So this V0 is equal to, so we got here epsilon R is equal to V0 by V. So V0 can be written as V into epsilon R. So I have substituted here. So we can rewrite epsilon naught epsilon R V by D. So what is V by D? Again E. So we can write epsilon naught E naught is equal to epsilon E. So by substituting this value here, so epsilon E is equal to, so this is the quantity due to polarization, so that can be equated to P. So polarization of charges. So now this P is equal to, we can write epsilon E minus epsilon naught E. So epsilon, you can substitute epsilon naught epsilon RE. So you take outside epsilon naught and E. So we get in the bracket epsilon R minus 1. So you can equate this to a new quantity known as chi, or susceptibility, electrical or electric susceptibility for the dielectrics. Okay, for a given dielectric. So that is given by epsilon R minus 1. So electric susceptibility is a measure of how easily a dielectric is polarized in an electric field. This electric susceptibility is nothing but epsilon R minus 1. Okay, so it is one and the same as the dielectric constant only. Actually, practically, we get, or experimentally we determine the electric susceptibility. That's why electric susceptibility is determined here. Now what is dipole moment? So mu, I have already defined the dipole moment. So it's a microscopic quantity, and when positive and negative charges are separated in a molecule or atom, we get a dipole moment in the presence of electric field. So the dipole moment of any atom or molecule is given by the product of the charge at one end of the dipole and the distance between the two charges. If dx is the distance between the two charges, so mu is equal to q into dx, so q dx. Polarization in terms of dipole moment. So polarization we can define in terms of dipole moment of a bulk dielectric material is defined as the total dipole moment per unit volume. So P is equal to N into mu, where N is the total number of dipoles or molecules present in the dielectric material and V is the volume of the material. So if we write N is equal to N by V, so we can replace N by V as capital N. So P, polarization, is equal to capital N into mu. Now what is polarizability? The dipole moment of an atom or molecule of a dielectric material is directly proportional to the applied electric field. So that we can write mu directly proportional to E, or mu is equal to alpha E, where alpha is the constant of proportionality and it is known as the polarizability of the atom or molecule, and it is a microscopic quantity. Since it is for atom or molecule, so it is termed as microscopic quantity. Now what are polar and non-polar dielectric materials? Polar dielectric materials are those in which the molecules or atoms possess spontaneous dipole moment permanent spontaneous dipole moment, or it is also known as permanent dipole moment. Even in the absence of electric field, so those dielectric materials are known as polar dielectric materials. So examples are all these. And non-polar dielectric materials are those in which the molecules or atoms do not possess spontaneous, that is, in the absence of the electric field, there won't be any permanent dipole moment. So, uh, only the dipole moment is induced, or it is present in the presence of electric field. So there is no permanent dipole moment. So examples are these many. Now, so there are three types of polarization. Depending upon the nature of the dielectric materials, we can classify the polarization into three types. So first one is electronic, second one is ionic, third one is orientational. So in electronic polarization, uh, if we consider any atom of the material, so that is in the absence of electric field, so the central nucleus consists of positive charges, and surrounding it the electrons are revolving in around the nucleus. Here we have considered Z electrons. Z is the atomic number, or the number of electrons present, okay, or the number of protons present. Both should be equal. Now, instead of considering number of orbitals, we have considered only a single shell in which Z electrons are revolving around the nucleus. You see here, O is the center of the nucleus, as well as C is the center of this electron cloud. So both are coinciding at the same point. Okay. So now, when an electric field is applied, what happens? This electron cloud is displaced. So there will be displacement of negative and positive charges, I told. So the electron cloud is displaced through a small distance. Then its center of mass will be uh, displaced, and we get, there is a small distance between the centers of masses of the nucleus as well as the cloud, electron cloud. So here, but when electric field is applied, the electron cloud of the atom is displaced opposite to the direction of the electric field, as shown in the figure 1b. As a result, the centers of mass of positive and negative charges are separated. They get separated. So this separation continues until the Lorentz force. Lorentz force is due to electric field. Okay, this causes the separation, and also it causes the formation of dipole moment. Okay, or dipole. So this separation continues. That means the separation stops when this Lorentz force is balanced by the Coulomb attractive force between the separated charges. The polarization arising from the dislocation of electron cloud due to electric field is called electronic polarization. So, from this electronic polarization concept, we can get an expression for electronic polarizability. Consider an atom of a dielectric material of nuclear charge D surrounded by a spherical electron cloud of radius. So this is electron cloud of radius r, and central part is having protons of plus Ze, okay, and this is minus Ze. Now the radius of this sphere is capital R, okay, and when an electric field, so this is in the absence of electric field, so when the electric field is applied, so this electron cloud is displaced, okay. So now the center is here for electron cloud, and the center original position, this is the center for nucleus. So this carries positive charge and this carries negative charge, and there is a small distance forming a dipole. So one end is having plus Zt and other end is having minus Zt. And now the charge density. So we have to define a quantity charge density rho, that is charge within this sphere per unit volume. Okay, that is known as charge density. So that is here the charge of this negative charge, let us consider minus ZE divided by 4 by 3 pi r cube. That is the charge density. So this is first equation. When electric field is applied on the system, the electron cloud experiences a Lorentz force. So that is in the opposite direction to the electric field applied. So this force is electric intensity of the electric field multiplied by the charge. Okay, so this is FL, opposite to the direction of the electric field, and displaces the electron cloud through a distance x. The displacement of the cloud stops when Lorentz force is balanced by the Coulombic attraction force of the nucleus and displaced electron cloud. Thus, minus ZeE, this is Lorentz force, and this is according to mm, Coulomb's inverse square law. We can write 1 by 4 pi epsilon naught. This is ZeE, the positive charge of the nucleus. And here, since there is a displacement of the electron cloud, we have to consider charge enclosed in the sphere of radius x. So this sphere we have to consider, okay, electron cloud charge. So that volume of this multiplied by charge density gives you the charge enclosed within the sphere of radius x. Okay, so divided by x square. X is the distance between the two charges, so that will be 4 by 3 pi x cube into this is the charge density. So by simplifying we get like this. So substituting this value in equation 2, we get minus the dE. So this is the simplification. So finally we get E is equal to this. From this we get the value of x, okay, by cross multiplying. Now this is from this we can write x directly proportional to E. So directly proportional to. Now electronic dipole moment of the system is given by mu E is equal to q into dx. So z e into x. Okay, so that x value is substituted here. So we get mu E is equal to this value. From this we know that mu E is polarizability multiplied by, this is electronic polarizability and this is electronic dipole moment, so into E. So by equating these two, we'll get alpha E is equal to this value. This is called electronic polarizability, and PE is equal to, in terms of dipole moment, n mu E, so is equal to n alpha E E. Yes, no? Now we can also write, we have got already in the definition of susceptibility, P is equal to epsilon naught epsilon r minus 1 into E. So by equating these two, so we get n alpha E is equal to this value. So alpha E can be written as epsilon naught epsilon r minus 1 divided by n. Thus the electronic polarizability, which is a microscopic quantity or property of the molecule, can be microscopic quantity or property of the molecule can be determined by knowing macroscopic quantity epsilon r, that is dielectric constant of the bulk material. Now ionic polarization, second one. This type of polarization takes place in ionic dielectric materials. Consider an ionic molecule such as sodium chloride. Sodium chloride is made up of sodium positive sodium ion and chloride negative ion. So since the two ions are already separated by a small distance, ionic molecules have a built-in permanent dipole moment, which is of the order of 10 raised to minus 29 centimeter. In addition, when ionic molecules are placed in an electric field, sodium and chloride ions are displaced in opposite directions until the ionic binding force stops the process. As a result, the dipole moment of the molecule changes, producing polarization. So this is in the absence of electric field. So here in the presence of electric field, these are separated and there will be a distance created, and this type of polarization arising from the dislocation of ions due to electric field is called ionic polarization. The ionic polarization is given by Pi is equal to N alpha I E. Now the last one is orientational polarization. So this takes place in dielectrics made up of polar molecules. So we have studied already polar dielectric materials. Polar molecules have permanent dipole moments. In such dielectrics, when no field is applied, the dipole moments orient randomly due to temperature. What happens? They will be randomly arranged. Hence, the net dipole moment is zero. When this dielectric is placed in an electric field, torque is exerted on the dipoles by the electric field. As a result, the axis of the dipole is rotated and tends to orient along the field direction. Okay, they get oriented towards the electric field such that there will be polarization. Net dipole moment will be finite. The polarization arising from the orientation of permanent dipole moments along the direction of electric field is called orientational polarization. So it is inversely proportional to temperature. We can directly write Po is equal to N mu O square by 3 kT E. So orientational polarization is inversely proportional to the absolute temperature, where alpha O is equal to mu O square by 3 kT we can write. This is orientational polarizability. So the total polarization, if we combine all the three types of polarization, this is electronic, this is ionic, and this is orientational, add all the polarizations and substitute the values. So P is equal to N into alpha E plus alpha I plus mu square by 3 kT into E. So this alpha E we know that is equal to 4 pi epsilon naught into R. Okay, so now this is the orientational polarization. When there is no field, all the dipoles which have permanent dipole moments are randomly arranged due to the thermal agitation, due to temperature. So there won't be any net dipole moment. But when the electric field is applied, all these are oriented towards the electric field. So we get polarization here. So net dipole moment will be finite and we get orientational polarization. So now let us end this class. Thank you.